Okay, so today we're going to take on the fundamental theorem of calculus, which will ultimately get us to an antiderivative. In order to do this, we have to construct a bit of a model, which derives from the idea of the Riemann sums. So if I have some function f of x, and I want to find the area of that function between the x value a and the x value b, so the area underneath that function between a and b, what the Riemann thing taught me was that I had to divide this into partitions. Yeah, so I'm going to divide it into a bunch of pieces. Okay, so I'm going to have a bunch of x values here. I'm going to say that a is the x value x0, this is x1, x2, x3. We're going to call this one xi. We'll call this one xi plus 1. This will be xn minus 1. And finally, xn. So we have n partitions, right? So this is how this kind of sets up. All right, so we're going to start declaring some things here. We're going to declare a thing called delta x. It is going to be equal to b minus a over n. This delta x is the width of each of these partitions. This means that the x sub I value has to be a, right? So we have to start at a. And then each x sub I is I times delta x away from a, right? So x sub 1 is at a plus delta x, x sub 2 is at a plus 2 delta x. So that should work there. And then we're going to declare this thing called x sub I star. Okay, and x sub I star simply is an element of the interval between x sub I and x sub I plus 1, chosen arbitrarily. Okay, so the idea here is that somewhere on this interval is this value x sub I star. And what we're going to do is we're going to use that value to find a functional value. So this value, this point here is x sub I star f of x sub I star. And we're going to use that to represent this entire partition. Okay? And the idea here is that the integral from a to b of f of x then should be the infinite sum from n equals 1 to infinity of f of x sub I star delta x. So why does this work? Okay, so the width of each of these rectangles is delta x. So there's my width. The height of each of these rectangles is that I'm going to pick some arbitrary point along there, and I'm going to make a rectangle. So that's the height, right? So if I take the height of the rectangle times the width of the rectangle, I get the area of the rectangle. Now, what I'm going to do then is we're going to have the number of partitions, though, not be a finite number, n, but n is going to be the limit as we go to infinity, right? Oh, there's a small glitch here. This should be I, right? We're going to add these up. So normally, we would just add them up until we get to n, right? But we're not going to n. We're going to let that go off to infinity. So if you kind of think about this, this is equivalent to the limit as n approaches infinity of the sum from I equals 1 to n of f of xi star delta x. So this is like my Riemann summing of all of these rectangles, but what we're going to do is just make the number of the rectangles go to infinity, and thereby we're going to actually hit the area under the curve. So this is how we can make this jump between a finite sum and the integral itself, the definite integral itself. Now, we have to make this tie here to the fundamental, using the fundamental theorem of calculus to the antiderivative. Okay, so we're going to get the fundamental theorem of calculus in two parts. So this is going to be part 1. Okay, so we have a function f. F is continuous almost everywhere on the interval a, b. Okay, so we're going to let g of x be this, what we said before, the integral function about a of f of t dt. And we're going to let that be on the domain AB. Okay, so then G is continuous on AB, and it is differentiable on AB, and most importantly, G prime of x is equal to f of x. And that's going to hold true for all x on the open interval AB. Alright, so what is this saying? It's saying that I now have a way to connect the derivative to the integral, right? So that if I take the integral of f, then I get g, right? And then g's derivative is f, which means that f has to be an antiderivative of g. So let's see if we can actually prove this. Okay, in order to prove this, I'm going to need what's called a lemma. Okay, and my lemma here is that if I can bind f of x between some little m and some big M for all x on the interval AB, then I should know that m times b minus a is, it's not strictly less than, it's less than or equal to, is less than or equal to the integral from a to b of f of x dx is going to be less than or equal to big M times b minus a. Alright, so proving this is a big step along the way of proving the fundamental theorem of calculus. So let's prove this. Okay, so we're going to establish that we have some function f, and it is always bigger than g for all x on a b. So x always dominates g. Okay, so from here it follows that the integral from a to b of f of x dx should also be dominating g, because if I'm always bigger, then the area under f always has to be bigger than the area under g. Okay, so since by assumption in our lemma little m is less than f of x and big M is greater than f of x, the following should hold, right? The integral from a to b of little m dx should be less than or equal to the integral from a to b of f of x dx, which should be less than or equal to the integral from a to b of big M dx. Okay, so this integral, m's a constant, right? And the width of this interval is b minus a, so this integral should be m times b minus a. It's just a rectangle. You can kind of work that out for a minute here if you'd like to. This one is going to stay where it is, right? So that's f of x dx. And this one is again just a rectangle, m times b minus a. So I've proven my lemma. Right, that's exactly what I needed to happen. So we're going to use this lemma as a tool when we actually now prove the fundamental theorem of calculus. So hang on to it. So here we go. We're going to prove the theorem. Proof of the theorem. Fundamental theorem of calculus, part 1. All right. So we're going to let x be some value on the interval, open interval AB. All right. So what does that mean? All right, that means since I'm on the open interval, there exists some h greater than 0, such that x plus h is also on the open interval AB. Because there always has to be some space between x and a and x and b, so I can add something to x and still not hit b, because that space has to exist. So there's a little trickery of mathematics there, but if you stop and think about that long enough and hard enough, you're going to see that that has to hold. Okay, so what we want to work with here is g of x plus h minus g of x. Okay, so remember from our assumptions here that g of x is the what's it called, the integral function, right? So just kind of recalling this, g of x is the integral from a to x of f of t dt, right? So this is going to be the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. And I can rewrite that as the integral from a to x of f of t dt plus the integral from x to x plus h of f of t dt minus the integral from a to x of f of t dt. Now, a quick examination of this says that these cancel out, and that can be simplified to the integral from x to x plus h of f of t dt. Okay, so why did I just do that? Well, I did that because then I can divide this through by h. Right, g of x plus h minus g of x all over h, and I can divide by h because h has to be greater than 0, is equal to 1 over h times the integral from x to x plus h f of t dt. Now, now let's think about why I may have done that, right? The idea here is this is the beginning of the derivative formula for g, right? Because if I take the limit as h approaches 0 of that thing, I get the derivative. So we're going to hold on to this thought. Okay, in the notes I called that star. All right, so let's see where we can go from here. And the next thing I'm going to do is I'm going to evoke the extreme value theorem. Okay, and we evoke that on the interval x to x plus h. The extreme value theorem says that on a closed interval with a continuous function, I have to hit a maximum and a minimum. Okay, so I'm going to do something here. I am going to call m the minimum, so on x to x plus h, I'm going to bind f between a minimum and a maximum. Okay, so I know that there has to exist some point u on x plus h where the f of u is minimum. So we're going to call that little m. Okay, and there's got to be a v on x plus h, where f of v is maximum, and we'll call that one big M. Aha, this is starting to sound like my lemma, right? So this means that M is clearly less than or equal to f of x, which is clearly less than or equal to big M. Now, by our lemma, we know that M times x plus h minus x has to be less than or equal to the integral from x to x plus h of f of t dt, which has to be less than or equal to big M times x plus h minus x, which, lo and behold, those cancel, and I have little m times h less than or equal to the integral and times big M times h. And if I divide through everything by h, which I can do because h is greater than 0, I get and in the end, m is less than or equal to g of x plus h minus g of x over h, which is less than or equal to big M. Aha. Well, that looks roughly familiar. Okay, so what's going on here? All right, so let's hold that thought for a minute, and let's get some more space here. How do I do that? Let's kind of take a big chunk of my paper here, and we'll delete that, and then we'll get rid of all this stuff, and we'll start working with this. So this is where we left off, right? All right, well, M was this f of u, and then I have this derivative piece floating around in the middle. And big M was this f of, big M was this f of v. So what we're going to do is we're going to take a limit. And we're going to take the limit as h approaches 0 of f of u less than or equal to the limit as h approaches 0 of g of x plus h minus g of x over h less than or equal to f, the limit as h approaches 0 of f of v. All right, well, h is the distance between x and x plus h, right? If that goes to 0, x and x plus h become a single point. So this is just going to become f of x. This is the derivative of g at x. And this, again, is going to become a single point, which is f of x. Well, if that sentence is true, then this, what we've called earlier in the class the squeeze theorem, right? So let's actually name that. You can go back and look that one up. Tells me that g prime of x is f of x, and lo and behold, we have proven the first part of the fundamental theorem of calculus, which tells me that if I take the integral, I should be taking an antiderivative. So that's like fantastic news. All right, so this is not really the really useful part of the fundamental theorem of calculus. We're going to get to that in a second, but we need this part first. Hence, it's called part 1. All right, so let's get part 2. All right, so let's look at the fundamental theorem of calculus, part 2. Okay, in part 2, this is a little bit easier statement. F is continuous almost everywhere on the closed interval a b, then the following is true. The integral from a to b of f of x dx is equal to big F of b minus big F of a, where big F is any antiderivative of little f. In other words, if I take big F prime of x, I get little f of x. Okay, so this is saying that if I take the antiderivative at b minus an antiderivative at a, then I get the value of the definite integral, which is the area under the curve. So not only do I have a connection between the antiderivative and the integral, but I have a way to calculate the area under the curve using those antiderivatives, which means I have a solution to the area under the curve problem using the idea of differentiation. So let's see if this actually holds, and we're going to prove it. So here's my proof of the theorem. Again, we're going to let g of x be the integral function from a to x of f of t dt. Woohoo. Okay, from FTC, Fundamental Theorem of Calculus, Part 1, we get that g prime of x has to be equal to f of x, right? So f is, if I take the antiderivative of f, I'm going to get g. Okay, so we know g is an antiderivative of f. Okay, so if f of x is an arbitrary antiderivative, then big F of x has to equal g of x plus some constant. Okay, so there's more than one antiderivative of every differentiable function or continuous function, but they all differ by a constant on AB. Okay, so we're going to proceed from here, and we're going to show that things work. First note, the integral from a to a, let's give that a name. Note that g of a, which is the integral from a to a of f of t dt, if I've gone nowhere, the area under that curve is 0. Okay, so let's take a look at this. Then f of b minus big F of a, the difference of the two antiderivatives, has to be g of b plus c minus g of a plus c, which is just, well, the c's fall out, so that's just g of b minus g of a, which is just g of b, which, well, let's see, that's equal to the integral from a to b of f of t dt, and there we are, we've proven it. We actually have that this integral has to be the antiderivative of b at b minus the antiderivative at a. Alright, so let's do a little bit of example work of computing a few definite integrals using this. Alright, so this is an example. Let big F of x equal 1/4 x to the 4th, right? Then we know that big F prime of x is x cubed. Okay, So the argument here is like I can calculate the integral from -2 to 1 of x cubed dx should be, well, should be 1/4 at 1 to the 4th minus 1/4 at -2 to the 4th, right? Because this is my f prime, so I take the antiderivative and I evaluate it at the two bounds, the b minus the a. Okay, so this is just a fourth. 2 to the 4th is 16, so this is going to be minus 16 over 4, which means the area underneath that curve is negative 15 over 4. So kind of thinking that through, the x cubed curve runs like this. -2 is out here, 1 is here. So we're talking about this area minus this, right? This part being negative, and that's the exact value of that region. It's going to be, if I take this piece minus that piece in area, I'm going to get negative 15 over 4. So that's kind of straightforward. All right, so let's look at one more quick example. All right, so let's say I have the integral from 0 to 1 of x squared dx. Well, an antiderivative of x squared should be 1/3 x cubed, right? 3 times a third is 1. Drop it by 1 gets me what I need. So let's say I'm going to take that from 0 to 1, right? Which means that this is 1/3 times 1 cubed minus 1/3 times 0 cubed, which is just simply 1/3. All right. So if I have this parabola, this is the x squared, and I'm measuring the area from 0 to 1 underneath that curve, the area of that space should be exactly 1/3. Okay, so this is a pretty useful thing here. I think that's why it's called fundamental. All right, so we'll be leveraging this over the next, several classes here.